There is this technique called batch normalization. And the idea is that you want to reduce the internal covariance shift. But what is an internal covariance shift? What does that mean? Usually, if you want to do any sort of regression or classification, even for shallow networks, even for classical machine learning, you need to normalize your data. It means that usually you subtract the mean and divide by the standard deviation of your data to make your data be in a nice range. Otherwise, the dimensions won't match, the units are going to be crazy, some of your features are going to be very small, some of your features are going to be very huge, and then it's going to confuse the training process. That you can do to your input images, and it is actually what you have to do. You subtract the mean. But the problem is that you can do with your input data. You can subtract the mean, divide by the standard deviation, and everything is going to work out. The thing is that when you push that through multiple layers, statistics of each layer, the input to each layer changes during training. So the statistics of your data are fixed, but the statistics of your first layer or the input to the second layer is going to depend on the parameters of the first layer. So the statistics depend on the parameters. So you cannot do the same trick. And this is a problem that's called internal covariate shift. So is this clear, the concept of covariate shift? Basically, the mean and variance of your intermediate tensors, the hidden tensors between layers, depends on your parameters. So it's going to change during training. As you change your weights and biases, those statistics change. They are parameter dependent. Is it clear? Yes or no?
That process is clear to me. It's not clear, though, why that's necessarily problematic.
Which one?
The shift in the images from being zero mean to having non-zero mean, it's not apparent to me why that's necessarily has a slowing effect on the deep network.
So yes, what I recommend is that you do a very simple linear regression, forget about images, and have your data be like this. One of the features, and your data have 3 dimensions rather than the huge dimensions that you have to deal with in the case of images. Let's say your data have 3 dimensions. The range of the first dimension is from minus epsilon to epsilon. Epsilon is very small. Okay. The range of your second dimension is from negative infinity to infinity, so very big. And these infinity numbers are machine infinity. And the third dimension has a range that's reasonable. I don't know, from negative 10 to 10. And then try to do your regression and see what happens. That's a good exercise.
That'll cause conditioning issues, right?
Yes. So you don't see it in your head, but you're gonna see it in your computer. Things are not gonna behave. They're not gonna converge.
Would you run into the same conditioning issues if the range of each variable were controlled and normal, but the mean was shifted? Does that also lead to the same conditioning?
Yes, as you shift the mean, you can do the same thing also. You can add a very large number to one of your variables and see what happens.
Okay, but I guess the problem is more clear now. Thank you.
So even for a simple linear regression, you have to normalize your data. Otherwise, things are not going to converge. because of numerical errors. And it's going to be ill-conditioned, exactly. But the problem is even worse when you have intermediate layers, and those intermediate layers depend on the weights and biases of the previous layer. Because now your statistics, the mean and variance are shifting with your data. So what they wanted to do in that paper is to change a usual, which could be convolution or which could be a fully connected layer. So these concepts are very general. You can apply them to convolutions, you can apply them to fully connected, you can apply them to RNNs. So batch normalization, but I'm introducing them in the concept of convolutions and fully connected layers now. The idea is that you replace your usual layer with a batch norm of the weights. This is the input to the layer. You multiply it by a weight. There is a way to ignore bias because batch norm has its own bias. I'm gonna tell you why. You can call that X, and then you push that through your nonlinearity to get your output. But what is batch norm? During training, we had a similar concept. You had to differentiate between training stage and testing stage. When we were dealing with dropout, you have a similar concept here. During training, you do one thing. During testing, you do another thing. What do we do during training? We usually take a mini batch of data. Let's say the mini batch has size M. This is a subsample of your data. Then your batch norm is going to be parameterized by gamma and beta. And the idea is that X goes in, and you want to get the output of batch norm out, whatever the output is. So you compute the mean from your mini batch. You subtract it from X. You divide by the standard deviation. And this epsilon is just a very small number, 10 to the power -8 for numerical stability reasons. So you subtract the mean, divide by the variance. But then what happens when you do this? You are getting rid of the bias. To add the bias back, you introduce some parameters, beta. Because whatever the bias is, you are canceling it out. So that parameter doesn't matter anymore. And you scale it up also, because the scale of this number is always going to be from 0 to 1. I mean, with mean 0 and standard deviation 1. So you correct the standard deviation. And whatever that you're seeing here are element-wise operations. So they are dimension-wise. This is a vector being multiplied element-wise by another vector. The mean is going to be a bunch of vectors. X is a vector, you're subtracting it, subtracting two vectors from each other, dividing two vectors by each other element-wise. The question is, are gamma and beta hyperparameters? No, they are parameters. So you can actually learn them. The same way that you learn W, you're going to learn gamma and beta through gradient descent. Does that answer your question? Okay, perfect. And X is an element of your mini batch. So this could be Xi, and you're doing the batch normalization for that. So the batch normalization is a function of your input and your mini batch. So it's a random thing. Why? Because your batches are random. And during training, it's okay for things to be random. We saw the same thing when we were doing dropouts. One nice feature that many people gloss over is that these are, when you do your gradient descent, the gradients of the parameters that are giving you x1 to xn are being passed through mu and sigma. So they are adapting. So there, yes, go ahead.
Real quick, mu and sigma here, they're indicating operators, right? So it's like mu is the mean of these data. Is that correct?
Yes, exactly. So
Okay.
on top of that, I'm writing the mean. So you
Okay.
take the summation
Mm-hmm.
of xi's, and then you divide by the size of your data,
Okay.
which is m. 1 over m, the summation.
Okay, thanks.
Variant, you computed the same thing. Any other questions?
I guess I'm unsure what this means when you say the gradients flow through mu and sigma squared.
So how do you get x1? x1 has a weight, and this guy is the input to your neural network, to this layer of your neural network. Even u depends on some parameters. Okay, when you compute x1, it depends on w and the rest of the parameters of your neural network, whatever that's coming before it in your layer. So the gradients are gonna go through these mean operations, and you're taking your gradients of w even through this.
Got it.
Here you're taking the gradient with respect to w, and you see it right here. Yes, this is x, that's x. So the gradient is going through x. But another observation is that the gradients are going through your mean operations and the variance operation. So the algorithm is sort of anticipating what's going to happen. It's going to take the cumulative effect of these weights changes on the outcome, on your loss. It's the total gradient, okay? This is a minor detail, but it's very important, because without that, if you put stop gradients here, in TensorFlow, you have an operation, it's called tf.stop gradients. If you do it on these two, you're gonna get into trouble. For inference, we don't want things to be random. We want things to be deterministic. So we need to have only one number here that is batch independent. And we want a number here that is batch independent. And you want to use that for every x. So during training, you can have a running average of these numbers, of these means that you're computing. And then you can have a running average of these variances. And just plug those two numbers here. And these are actually not numbers, these are vectors. Plug those two vectors here.
Doesn't that converge to the average of all the data?
Yes, it does. So it does it in a smart way. So yes, the idea is that you take the expected value of your mu, which is basically your running average. And then this is you take away the bias and you compute the running averages of your sigmas. So these are the two numbers that you put in inference to take care of your network becoming deterministic. Now your network is deterministic, you can put it into production. The same way that gamma, beta, weights, and biases are going to be fixed during inference, mu and sigma are just going to be a bunch of other vectors.
But they're informed from your training data, right?
They are informed by the training data, yes. So these are not trained. Mu and sigma are not trained. They are not trainable parameters. They're just mean and average and standard deviation. But beta and gamma are trained, and W is trained.
Right. I think I'm a little confused about the X's. Are those coming from your like image at runtime, or what are those X1 through XM under the inference section?
So let's go back to one of these structures. Maybe this structure is a good one. The first X is going to be your image, okay? But then you're having 256 images that you're processing at the same time. Why? Because you're going to run that on a GPU, and on GPU things are parallel, so you can run them fast. It's actually much better to do things in mini batches than do them one at a time, okay? So you have 256 images that go into your first convolution, and then out comes 256 tensors of this size. And then you take the mean and standard deviation of that tensor. And then before you go to the next layer, you subtract the mean and divide by the standard deviation before you go to the next layer. Now I'm renaming X to be whatever the outcome of this layer is. So the input to each layer is being called X, and the output is whatever that's coming out, okay? So these X's depend on the parameters of the previous layer. Is that clear?
Yeah, that makes sense.
So yeah, X keeps changing, and it's parameter dependent. It depends on the parameters of this convolution. It depends on the parameters of these two convolutions when you have one X here going through your inception. That's why these means and variances are batch dependent.
So the very first, let's say, image that we're conducting inference on after training, what is the value of mu?
The first, what do you mean?
So we've trained, we've got a whole bunch of X's that go through it. We do this running average. We say, good, it's fully trained. We got all our parameters. Now I want to classify an image. Where do these X1 through XM come from in the inference stage? Are they just the most recent X's that were passed through during training?
So no, that's why during training, you keep a running average of your mean and variance. And then during testing, you don't need X1 to XM anymore.
You just take whatever the
running average.
The last running average when we stopped training was.
Exactly.
Okay.
Yeah, the last guy, the inference, the batch norm, as I see in my notation, it doesn't depend on your mini batch.
Yeah. So we just freeze the running average at the last stage of training. That makes sense.
Exactly. But your batch norm for training depends on mini batch. This one is random. This one is not. This one is deterministic.
So the X that's input to that batch norm is not the same X that's in the next line with the like mu definition. I think that's where I was getting confused, is the X's to define mu are from training, but the X at batch norm is sort of a new data.
No, look at this. During training, you're doing a batch norm of some X. It depends on some two parameters. You have the same thing here. Yes, it's the same X, gamma, and beta. But then there are a bunch of other X's that are your mini batch. You don't have it during inference. So the notation to me seems consistent.
Can I say, so I think that for me, the confusion is in training, everything is happening in parallel. And so like the U is the input to that layer, which is also a mini batch. and then we compute WU for each data point in that mini batch, and that's X1 through XM. And then for each X1 through XM, we can do this batch norm based on all the other X1 through XM. And
Yes.
that's all happening in parallel.
Yes. So if you had a normal neural network layer, you would have U1, and it's going to give you Z1. You would have U2, it's going to give you Z2, and so on. But with batch norm, your input, which is U1, is going to depend on U2, U3 up until UM through the batch norm, through this mean and variance.
And so this is entirely dependent on having like GPU capability. Like you can't do this if you're not training in parallel, sort of.
Exactly. So that's why GPUs are so popular.
Okay.
It's one is mini batches, the other one is these convolutions. Many of the operations are going to be done in parallel, as they are linear algebra operations.
Mm-hmm.
And matrix multiplication, you can do it in parallel. Any other questions?
I had a question about the gamma and beta parameters.
Mm-hmm.
So when you are training or an inference, they should stay the same for both training and inference.
Yes.
Correct? Okay. And is it dependent on the data? What is the best value of gamma and beta? Or how do you determine those values?
Gamma and beta and W are determined through gradient descent. The first lecture that we had in this course, mu and sigma are determined differently.
Right. Mu and sigma are different. Yep.
And whatever that I'm talking about here is layer-wise. It's just one layer of your neural network. This is going to happen for every layer.
Thank you.
Any other questions?
Thank you. Have a good weekend.
You too.
Thanks.
Sure. Okay, if there are no more questions, see you next time.